I feel obligated to inform everybody that I recorded this video 2 separate times now, both with my mic off. And this is the 3rd time now that I am attempting to cover impedance. So hopefully I can get through it, and hopefully my lack of enthusiasm does not disturb you. So I want to talk about impedance. Actually, I was going to sit here for a second. Basically, if you remember from DC circuits and from EE220, I covered voltage and current and resistance. And then once I covered the 3 of those, I covered Ohm's law. And from there, we were able to start solving circuits using Ohm's law. Well, the case is the same for AC circuits. However, I've covered the fact that voltages and currents in AC circuits are going to be represented by sinusoids. We can use phasor analysis, we can use complex analysis in the rectangular coordinate system to do the math. I haven't shown any circuits yet though, because we still need to cover the concept of impedance before we can actually solve some circuits. So let's get through this. Pretty straightforward. Let's just cover, so I'm going to cover what is impedance, but first I want to do a quick refresher on resistance and what it is and kind of how it works. So let's just say I have a 1K resistor here, and let's say I apply some voltage, something like 10 volts across my resistor. That voltage is going to give rise to a current I, which I can say is equal to the voltage divided by the resistance. That would give me 10 milliamps, right? 10 volts divided by 1K. Well, what would happen if I increase my resistance here? Well, if I increase it, let's say I increase it to something like 10K, I decrease my current by a factor of 10 as well. That means that for the same voltage, as I increase my resistance, I get less current, of course, because that's what resistance is. It tells us how resistive something is to the flow of current. For the same voltage, more resistance results in less current. The same is the case for impedance, except you can think of impedance as the AC equivalent of resistance. The same way that resistance and voltage and current in DC circuits follow Ohm's law, V equals IR. That is Ohm's law. Impedances also follow Ohm's law. Okay, so I usually draw my impedance as a box. It is denoted by the letter Z. And impedances also follow Ohm's law. And like I said, impedance is the AC equivalent of resistance. So if that was the case, I could write my Ohm's law as V is equal to I times Z. Okay, where Z is the impedance of an element, not necessarily the resistance. I say necessarily because it could be the resistance, but impedance is even further than resistance. Resistance is a one-dimensional quantity, right? It is only a real value. It's either, 10 ohms or 100 ohms or 100 kiloohms. There is no complex portion, where an impedance actually has a real portion plus J times an imaginary portion. And actually, it just so happens that the real portion is called the resistance, and the imaginary portion is called the reactance, okay? This is the resistance. This is the reactance. And so what a resistor really is, it is an impedance that has no imaginary portion. It has no reactance. It only has resistance. So you can think of a resistor as just an impedance with a value of R. And I'm going to get into that in the next slide, so let me just go there real quick. You can see here I have the impedance of passive elements, the resistor, the capacitor, and the inductor. The impedance of a resistor is simply R. So if I look at my box, this is my impedance Z. In this case, it would just be a resistor. What's inside the box is just a resistor. I draw the box kind of like just because an impedance could be a resistor or a capacitor or an inductor or any combination of those elements in parallel or series. But for the case where I'm just looking at a resistor, the only thing I would have here would be the resistor inside my box. And so in this case, the impedance would just be the resistance R. However, notice that for a capacitor and for an inductor, the impedance is actually dependent upon the frequency that we're at. So if I have my box here, my impedance, what's inside my box is just a capacitor. The impedance of the box, or of the capacitor, would be equal to 1 over J times 2 pi F times C. And so you can see that not only is my impedance here a reactance, it's a reactance because it's dependent upon frequency. It's also a complex value. It has a J in it. So I can rewrite that if I use my complex number rules as minus J over 2 pi FC, or I can write it as minus J over omega C if I wish. But just note that this impedance is dependent upon frequency. It's actually a function of frequency. So my impedance changes as my frequency changes, okay? That's a very important concept. The same for the inductor. The impedance changes as the frequency changes. And if you remember, I did talk about the fact that a capacitor is an open circuit for DC. That's because if I let my F go to 0, which is DC, this whole thing goes to 0, and the impedance of a capacitor goes to 1 over 0, which is infinite. And infinite impedance is an open circuit. So at F equals 0, the capacitor is an open, right? The same for the inductor. At F equals 0, which is DC, the impedance goes to 0, which means the impedance of my inductor would be 0. It would just be a wire, which is exactly how we said an inductor behaves at DC. Okay, so just for completeness, let's say inside my box here, I've got, let's say inside my box here, I've got an inductor. And I will say that the inductor impedance is J omega L, or it could be written out if I replace omega with 2 pi F, as J 2 pi FL. And of course, the important piece here is that these impedances, the impedance of the capacitor and of the inductor, are dependent upon frequency. The impedance of a resistor is not dependent upon frequency. It does not have a J in front of it. And so if I had two elements in series, I'm going to talk about that in the next slide, but just so you know why I'm talking about reactance here, this is a reactance. This is a resistance. And again, impedance is the sum of resistance and reactance. That's what I had here. If I add my resistance and my reactance, I get my impedance. So for a resistor, it would basically be R plus J0, which is just R. For a capacitor, it would be 0 plus J omega, 0 plus 1 over J omega C, or just J omega C, right? Or 1 over J omega C, but the real part goes to 0. Here, the imaginary part goes to 0, okay? I'm kind of rambling at this point, but hopefully you understand what I'm saying. The important piece, and you know what, I'm not going to talk about series yet. I'll talk about that in the next slide because that's what the topic is of the next slide. Hopefully this is clear. If you have any questions, feel free to ask. One more time, I'm just going to say that the important piece is that the resistance is the part of the impedance that is not dependent on frequency. The reactance is the part that is dependent on frequency. So capacitors have a reactance, which because they are dependent on frequency. Inductors have a reactance because they are dependent on frequency as well. Okay, so I'm going to go ahead and end this video right here.